Greetings and welcome to another installment of Quantile. This is 22 in our basic application series. I have been reminded that I am under contractual obligation to mention that the following installment of Quantile is being brought to you by our new parent organization, Slob Global Corporation. This time around, we're going to power on with part 3 of our practical series on hypothesis testing of a single proportion, picking up right where we left off in part 2. So we'll do a quick recap here. Our friend finds themselves in possession of a mysterious, purportedly loaded coin. To test this claim of loadedness, we fashion a decision theory style statistical test. We use the normal approximation, or if we prefer, the normal model. A standard normal distribution to approximate the sampling distribution of our sample statistic proportion of heads. In our first step, we set our test significance level to 0.02 or 1 in 50, which gives us our test stat critical region, or sometimes called our rejection region. In our second step, our observed sample proportion of heads was 30 over 50. Using this value, our calculated test stat z was about 1.41. This value is not in our critical region, and so as a consequence, we fail to reject the null hypothesis. To transform our sample statistic into our test stat, we use this function here. So let's keep peeling back the layers. What is this? What are we looking at here? One piece of good news is that, like so much delicious nigiri, we can break this down into bite-sized pieces. Another piece of good news is that these pieces do reappear in many statistical applications, including other types of hypothesis tests. So understanding this particular application is certainly going to help us down the road. So let's start by zooming in on the numerator on the right-hand side, the top of the fraction. So what do we see here? What is this? Well, very simply, it's a difference between two quantities. We have our observed sample statistic proportion minus our hypothetical value of the population proportion, or the value of our population proportion under the null hypothesis. We can think of this difference as a measure of how far away our observation is from our assumed value in either direction. If our observation is larger than our assumed population proportion, this difference is going to be some positive number. Conversely, if our observation is smaller than our assumed population proportion, this difference is going to be some negative number. And of course, needless to say, if our observed sample proportion is the same as our hypothetical proportion, then this difference, the numerator on the right-hand side, is simply 0. The denominator here is where really much of the action is. This entire quantity is called our standard error. The value p times the quantity 1 minus p may look familiar. We visited this back in our proportions yet more installment. It is the variance of an indicator attribute. The variance in our imaginary infinite population of coin flips of the indicator attribute is heads. If the population proportion is 1/2 of the value under our null hypothesis, then this value is 1/4. And here is simply our sample size. In this example, the total number of flips or trials, 50. One really important thing that I want us to be aware of here, speaking loosely or conversationally, we can think of the standard error as an evaluation of the amount of volatility, uncertainty, or imprecision even of our sample statistic. Accepting the case where our observed difference in the numerator is 0, if our standard error is relatively large, then the magnitude of our test stat, our z-score, will be relatively small. Conversely, if our standard error is relatively small, the magnitude of our test stat will be relatively large. So let's grind this out. Let's just go ahead and plug our values into our function, and lo and behold, we sort of already knew this. Our trusty function returns to us a value of about 1.41. Before we close out this edition, I want us to consider another but mathematically equivalent way to express our function f. With a little bit of algebra, we can rewrite our function like so. And I showed the mathematics here to provide rigor, but if you're not comfortable with these operations, it's really not worth worrying about at this point, I don't think. The big message or takeaway is that this function is equivalent to the one we were just looking at in terms of inputs and outputs. And I actually much prefer this representation, although it is not commonly utilized in introductory stats texts. And there's really two reasons I like this representation, and perhaps you will come to like it as well. The first is that the quantity here is a measure of precision. That is, the precision of our sample statistic under theoretical random sampling given a true null hypothesis. And I think that for most people, thinking about precision, or more loosely, certainty, is more natural than thinking about variance, or more loosely, volatility or uncertainty. The other reason I like this is, well, this representation involves one less division. It's just a little bit easier to look at and think about. Square root of the precision goes up, magnitude of our test stat goes up. Square root of the precision goes down, magnitude of the test stat goes down. Nice and simple, no problem. Make sure to check out part 4, and that's it. That is going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more quantile.
The preceding installment of QuantSlob was brought to you by the good, honest, wholesome, hard-working people at Slob Global Corporation. At Slob Global, we put the SOB back in slob.